compounds. I just want to start from one end. People, the alkanes, we say they form what is known as a homologous series or a homologous group. That is just simply a group of compounds that have got similar properties. We say they have the same general formula and same general properties. We said the general formula for the alkanes was CnH2n plus 2, where n is any whole number. So if I have 5 carbons, I will have 2 times 5 plus 2, 12 hydrogens. Are you with me? Yes? Diesel is also an alkane. Yes, yes. They are mixtures of carbons. Petrol is between, I think, 5 and 10 carbons, and diesel is slightly longer. Yeah, but they all burn. Yes, because, yeah, but if you look at the general tendency of properties, petrol is a smaller molecule. Diesel is a bigger molecule. So the bigger the molecule, the higher the boiling point. So diesel, well, is a liquid that doesn't really want to evaporate. But petrol does, because it has a lower boiling point. You understand? It's got to do with the molecular structure, but they behave similarly under similar conditions. They can all be burned to get carbon dioxide and water vapor. All right. Okay, so we said they were saturated. What did that mean? Yes, that between the carbon atoms, there are single bonds, and each carbon is bonded then onto the maximum number of hydrogens. Just general boiling points increase with increasing molecular mass. We saw that in the fractionating column as well. The smaller molecules, the gases, came off at the top, and down at the bottom we got the lubricating oils and the fuel oils, which were larger molecules with higher melting and boiling points. We had a look at did we have a look at the combustion of the alkanes? No. Okay, because that is the next thing we must have a look at. Now, we've already said the alkanes can act as fuels, which means we can burn them and they produce energy, carbon dioxide and water vapor. When we have enough oxygen, we get complete combustion. If there is too little oxygen, we get incomplete combustion. All right? Now, when we're going to have a look at the combustion of the alkanes, okay, yeah. The first one is methane. Methane looks like this. Yeah, we did that now. Okay. The second one is ethane. All right. Leave propane for a moment. Combustion of methane. When methane burns, what do we get? Carbon dioxide and water vapor. CO2 and H2O. Is that right? Okay. Same with this one. If this one burns, what do we get? CO2 plus H2O. Quickly take a pencil and a piece of scrap paper and try and balance them. Just quickly. The first one should be easy. But the second one, some of you might run into problems. Have you got it? No. Okay, let's quickly have a look at them. Let's do the first one, because the first one's easy. You shouldn't have problems with the first one. 1 carbon, 1 carbon. 2 oxygens, 1, 2, 3, 4 hydrogens, 2 hydrogens, we need a 2 there. But now, how many oxygens? 2 plus is 4, so we need 2 over there. Are you all with me on that? That's not a problem. Okay, but this one, how many carbons? 2. So we put a 2 in there. How many oxygens? 2, 2, 4, plus 1 is 5. Let's have a look at the hydrogens. 1, 2, 3, 4, 5, 6 hydrogens. How do I get 6 hydrogens? I will need 3 there, but does this solve the problem with the oxygens? We have 4 and we have 3, that gives me 7. How do I get 7 oxygens? Well, technically, I would need 3.5. Okay, can I have a half? No. So what you're going to do is you're going to multiply everything with 2. Because when you have an equation, what you do to the left, you must do to the right, and you don't change it. No. So over here we will have 2. Over here we will have 7. There we will have 4. And here we will have 6. Okay. People, it just works like this. When we balance the combustion reaction of an uneven number of carbons, it's easy. It works out easy. But if you have an even number of carbons, then it's difficult to balance. So if I want to be nice, I'll give you the easy one. I'll give you an example with an uneven number of carbons. And if I want to test and see, can you really do balancing, I'll give you a number with even numbers of carbons. Yeah, it doesn't mean I don't like you. Have a look at propane. Propane is C3H8. Butane is C4H10. Okay, so quickly do the balancing. That one should be easy. Look at this one. The uneven number. 3 carbons. 8 hydrogens. So we've got how much? 6 plus 4 is 10. Gives us 5. That shouldn't be a problem. No. But this one, 4 carbons. So we go with the 4 carbons. 10 hydrogens. So we go with the 10 hydrogens. But now if we look at the oxygens, we have 8 plus 5 is 13. So how do I get 13? I will need 6.5. But I can't have a half, so I will need 2 there. I will need 13 there. I will have 8 there and 10 there. You multiply with 2, just everything. Okay. All right. So, over here, isopropane is a structural isomer. We've had a look at that. People, what does isopropane look like? Methane, ethane, propane with a branch on it and filled up with hydrogens. Okay, isopropane. I don't need to say more about that. We did that in the last period. All right. Now, in this next section, we've already had a look at the combustion of alkanes. We know they are used as fuels. When they burn, they give us carbon dioxide, water, and energy. During incomplete combustion, it is important to know that we get carbon and carbon monoxide together with the water and the energy. Some of the other reactions of the alkanes is something called substitution. Now, if I have a hockey team and I want to substitute a player. What must I do? I must take one out and I must put another one in. So in terms of substitution reactions with alkanes, we have to take something out and put something else in. For example, let's say I have got ethane plus, let's take bromine. Actually, let me write the bromine like this. Now, I want to do it in a different color as well. Let's go and do that. And then I want to go there. And I want to go there. Okay. We must take something away, because all the bonding places have been filled. The easiest would be to take a hydrogen out, okay, and add a bromine, and that forms HBr plus my halo alkane. Can you see that? We've taken something away and we've put something else into its place. Substitution. Now, the alkanes are not very reactive. Sometimes we need to encourage the substitution reaction. It sometimes goes a little bit slowly, but we can make it happen. What would the name of this compound now be called? Well, we no longer have ethane because we've got a bromine stuck onto it. This thing would be called bromoethane. Okay. Now I can repeat this process. Okay, and I can add another bromine. Well, I can add it on any of the places. You can do it step by step and you can remove all the hydrogen. So if I put a bromine there, what would this thing be called? 1,2-di bromoethane. Okay? If I put another bromine there, what would its name be? 1,2-tri bromoethane. Can you follow that? Okay, they won't go into big detail with it, but if you can follow the trend, that's okay. Do you understand? Because on carbon 1, I have 2 bromines, okay, and on carbon 2, I have 1 bromine, okay. So we list them from the lowest possible numbers. All right. Okay, so that then, this thing is called a haloalkane. And haloalkanes are a fairly useful group of compounds. So when I do a substitution reaction, let's just rewrite it. Hydrogen, hydrogen. With bromine, we will get bromoalkane. It's just, it can go on any carbon, all right. It can be controlled, but it's not part of our syllabus to know where it goes, so we just stick it onto the end, plus hydrogen bromide. Yes, they do slightly change, okay. Things a little bit like reactivity, and there is a couple of things that changes with it, all right. But the extent of our syllabus, it becomes very specific with catalysts and temperatures and pressures and so on. We don't go into that, all right. So when we do substitution with halogens, we will do it like that. Remember, don't forget that is also formed a hydrogen bromide, okay. Now, we can do a substitution reaction with water, and the product that is formed is an alcohol. Now, the alcohols also form a group of organic compounds, and their functional group, how do I recognize an alcohol, is an OH group on the molecule. All right. Now, once again, it can have more than one OH group, and that OH group can really go anywhere on the molecule. For our purposes, we usually just stick them onto the one end. Okay. If I go and have a look at the substitution reaction of an alkane with water to form an alcohol, let's take a different one. Let's take propane. Okay, so methane, ethane, propane. There, and hydrogen for the alkane. There we go. And we must add water. Now I'm going to write the water like this. OH. I want to do it like that. Okay. What is going to happen? Well, we need to break off a hydrogen. I don't think one is going to go. Okay. So let me get a smaller rubber. I'm going to take off that hydrogen. And I am going to get, undo. I'm going to take that one, and it's going to go there. And the hydrogen that I broke off is going to go there. You follow? Okay. So, how will I show the addition of, seriously, the addition of water onto an alkane? Well, just very simply, we take any alkane. We did this one with propane. There. Okay, and we are going to add water, HOH. I'm going to write it like that. And what are we going to get? Well, yeah, I didn't write it as an equation. Okay, so what is going to happen? Let's break off that hydrogen, and we are going to end up with OH, and the original structure that we had, plus what are we going to end up with? There's a bit of hydrogen. All right. The substitution reactions. We have done two substitution reactions. The one is with halogens to form a haloalkane. The other is with water to form an alcohol. An alcohol functional group is OH. We'll have a look at the group in a little bit. The next reaction of an alkane is called cracking, catalytic cracking. Now, cracking is just very simply you break the molecule. So when I crack an alkane, I get an alkene and hydrogen. Okay, so take any alkane. Just take methane, ethane. And I am going to crack it. And I am going to get count the hydrogens. 6, 4, 5, 6. Okay. This thing with a double bond over here is an alkene. Okay. That's the next group of compounds that we will be looking at. Alkenes. So alkanes can undergo combustion reactions. They can undergo substitution reactions. In other words, I can take something off and I can put something else on. The ones that we most often do is with the halogens and with water. If it's a halogen, I get a haloalkane. If it's water, I get an alcohol. After substitution, we can go and crack an alkane. What does catalytic cracking mean? Well, we break up a large molecule into an alkene and hydrogen, or you can break it up. If you have a very long molecule, it's broken up into an alkene and an alkane. It depends. You just, once again, it can be controlled using specific catalysts, specific temperatures, specific pressures. The syllabus does not go into that. All right. Yeah. Yes. We'll have a look at them in a moment. You do get with more. We just work with the one. Okay, we just keep it simple. All right. I'll come back to this one. It's just the next compound we will have a look at. All right. People, after cracking, we get something called polymerization. Now, polymerization is they simply take one molecule and they make it stick onto another one to form long chain-like molecules. By means of polymerization, there is an infinite number of compounds that we can make. Because every time you add an extra molecule onto it, if we used ethane or ethene, then polythene is made from ethene that has been polymerized. Yes, yes, okay. Catalytic cracking, we've just had a look at that. Breaking up of large molecules can be broken down into smaller molecules, and then something called reforming. We don't go into that at this point. Can change the shape of the molecules. Now, who knows what Sasol did? What was their big breakthrough? They used coal, technically. That was to make petrol. How could they do it? What does coal consist of? Carbon. They do. That was the later research. Yes. But how can they do it? How could they do it? They took carbon, which is coal or coke, which is carbon, and they made the one carbon, instead of forming a crystal lattice, stick the one onto the other, and then they added hydrogen to it. Water is probably the source. I don't know what their source of hydrogen was, but added hydrogen to it, and from that they could make petrol. No, the previous history was crude oil is distilled, that different fractions are used. And then I think when they started working with it, they discovered, but we can break up longer molecules because it's desirable to have carbon 5 to carbon 10 in a chain for petrol. That's the greatest demand. And that is how they supplied it. But that is basically where Sasol's research comes in. All right. Now Sasol is also a large company, and they are into plastics and a whole lot of stuff. Okay. All right. So that then is the last three processes: polymerization, catalytic cracking, and reforming. That's basically what Sasol did. Okay. Our next group of compounds then after the alkanes are the alkenes, and the alkenes are unsaturated, which means they have a double bond, or, well, the alkynes have a triple bond, but we don't do alkynes. But we find that there are double bonds between consecutive carbons, which means that each carbon is not bonded onto the maximum amount of hydrogens. We say it is unsaturated. The first alkene in the group, what would it be? Would we get methane? Why not? We need two carbons with a double bond. So methane only has one carbon. So the first alkene is going to be ethene. Yes. Do you understand? Okay. What would propane look like? Like that? Would it matter if the double bond went there? No, it would still just be propane. How many places has carbon got, bonding places? Count them. Yeah, on that side. No, can't. It's got 4 bonding places. 1, 2, 3, 4. Yeah? This carbon has got 4 bonding places. 1, 2, 3, 4. That carbon's got 4 bonding places. 1, 2, 3, 4. All right, carbon has 4 bonding places. It was a good question. Yes. Like that? It's a mirror image of the first one that I've drawn. It is still just propene. All right, now, structural isomers. Because when we get to butene, there's the one. Yes? If we go to butene, 1, 2, 3, 4. 1, 2, 3. I'll show you now in a moment. Hydrogen, 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 hydrogen. Normally we would have called it butene. But butene can look like this as well. Let me do it in a different color. One, two, three, 4. 1, 2, 3, 4. 1, 2, 3. There. These two compounds, the red one and the green one, would have the same formula. It would be C1234H8. Okay? But they are not identical. In the one, the double bond lies on the end, and the other one, the double bond lies in the middle. So we need to be able to name them in such a way that we can distinguish between them. The easiest way to do that is to number the carbon where the double bond is, so that the double bond gets the lowest possible number. So it would be between carbon 1 and 2, and on this one, 1, 2, 3, 4, or 1, 2, 3. So it's still between carbon 2 and 3. So the red one, we will call but1 in, because the double bond lies by carbon 1. This one would become but2 in, because the double bond lies between carbon 2 and carbon 3. Would we get but3 in? No, because but3 in would be a mirror image of that one. Okay, if you flip it over. All right. Are you with me? All right. Now, because of the fact that our alkenes are unsaturated, we said the alkenes, oh goodness me, where am I? They form a homologous series, same general formula, CnH2n, and they are more reactive than the alkanes. The reason for that is, people, when we have a double bond, the second bond is easier to break than that first bond. So if I have single bonds between carbons, they're fairly strong, but if I have a carbon with a single and onto it comes a double bond, then that second bond is easier to break than a single bond. And this makes that the alkenes are more reactive, they are more willing to react than the alkanes. Okay? They will react slightly faster and slightly easier, where, for example, the alkanes, I would have to heat them, expose them to sunlight, add a catalyst. The alkenes would just go naturally. Yes? Yes, because of you need to break 3 bonds to get separate atoms. But now we're opening up a bonding place. We aren't getting separate atoms. Do you understand? From the inorganic chemistry, if I have, for example, oxygen, it's fairly stable. I need to break a double bond to get separate oxygen atoms in comparison to hydrogen, where you have to break 1 bond to get separate atoms. We don't want separate atoms here. We want to open up a bonding place. Okay, that's the difference. Yes. What is going to happen? How will they react? Well, the first type of a reaction with an alkene is simply called addition. If I add a player to a field, I put him onto the field. All right? So what do I do to be able to add something onto an alkene? If I add hydrogen, what is going to happen is I am going to break open that double bond. There are my original hydrogens that I had. there, and a bonding place will open up there, and I will get a hydrogen. Take that one away. And a hydrogen over there. I've broken that double bond. The moment I break it, a bonding place opens up on each carbon on either side of where the double bond was. Remember, a chemical bond minimum requires 2 electrons to be shared. If I break that bond, 1 electron goes to the one electron goes to the other, so I've opened up 2 bonding places. The alkenes form a homologous series. General formula, CNH, 2N, and what was important here is they are unsaturated hydrocarbons. All right. I'm not going to go and look at all of the structures that we did the other day. That stays the same. Then we started and we had a look at the chemical reactions that they can undergo. Now they are hydrocarbons, so they can burn and they will form carbon dioxide and water vapor. Then I said to you, they are more reactive than the alkanes, because when the alkanes have to react, they have to undergo substitution. We have to take away something and put something in its place. But with the alkenes, we find that they are much more reactive. They can undergo addition reactions, which means we don't have to remove something before we add something on. What we go and do is we go and break the double bond. Now onto an alkane, we can add hydrogen, we can add halogens, all right, and we can add water. Yes, yes, okay. Now, did we have a look at the substitution reaction of the alkane? No, the alkane. When we were busy with the alkanes, did we do the substitution reaction of a halogen to form the haloalkane? Okay, we took away a hydrogen and we added in an atom of the group 7 element. Yes, okay. Now, with the alkenes, we add. How does it work? For example, I will have ethene there, and I am going to add hydrogen. Let's go plus, and I'm going to do hydrogen like this. Let's go like that. Okay? Now what is going to happen? We are going to break the double bond. So we will get the original structure that we had, and on either side where we broke the double bond, a bonding place opens up. On the one goes the hydrogen and the other goes the hydrogen. So yes, when I do an addition reaction of hydrogen onto an alkene, the product is an alkane. Yeah. So we can go from an alkane, we can crack it to an alkene, and from an alkene we can go back to an alkane. All right. Now, in the same way, we can add a halogen onto an alkene. Let's go and do like that. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And we have those hydrogens on it. And let's say we go and add bromine. Now, once again, I'm going to draw the bromine BR, it's diatomic, ne? Okay, so you understand when I do it like that. All right, now we are going to break the double bond. The moment we break the double bond, we find that was the original structure there. Carbon, hydrogen. All right, there was the original structure. If we break the double bond, two bonding places open up there and there. So bromine and bromine. When we worked with the alkane, we got the haloalkane plus hydrogen bromide, for example. Eh? Yeah, we don't have anything extra because both the bromines can go and stick on the molecule because two bonding places open up. Yes. All right. Yes, you could, but your syllabus limits you. Yeah, we just do the halogens. You could, for example, have hydrogen bromide. You get a haloalkane again. Okay, it is possible, but we don't do it. All right. Okay, so now the product once again is a haloalkane. If we looked at the naming of this compound, what would its name be? For example, this is propane. Yes, 1,2-dibromopropane. No, it's saturated now. Yeah. So this is 1,2-dibromopropane. Yes. Yes. Yeah. It's still an alkene. Yes, 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 yes. Yes. No? Yes. You get many variations. Our syllabus is simply one double bond in the molecule. You can have 20 double bonds in the molecule. Polyunsaturated, what does it tell you? Many unsaturated bonds. So plant oils are polyunsaturated. They've got many unsaturated bonds. Okay, it's just, we only do it very simple. Okay, so if you go and do organic chemistry at university, then you will definitely go and have a look at the 2, 3, 4, 5 double bonds within a molecule. Okay, and you can control with catalysts and pressure and temperature, you can control where they go and which ones are broken. It becomes very specific, but it's very specific. Yes, you can control that. Yes, yes, yes. Okay, that's why it's an infinite chemistry. I mean, it's one of the most rapid growing departments of chemistry that there is because it's infinite. Yeah. Okay. Catalysts, temperature, pressure. Yeah. Yeah, and a lot of it is trial and error until they get a desirable compound and they figure out how did they do it and, yeah. Okay. All right. People, the next section is the reaction of haloalkanes with water. Now, bromoethane, what would bromoethane look like? Methane, ethane, one bromine on that. Okay, bromoethane with water, if it is boiled together in the presence of an alkaline substance, something like sodium hydroxide. No, we just take it on the edge. Once again, we simplify it. Well, this is going to be either where it goes, it's going to be one bromoethane, do you understand? Okay, so when we go and heat this haloalkane with water, you boil it together in the presence of an alkaline substance, we get a new product. Ethanol. What is ethanol? It's alcohol. We drink it in beer and wine. Okay? And the alcohols are the next group of compounds that we will have a look at. Okay. Over here. It's going to react with water, and we are going to get an alcohol. That is an alcohol. Yes. All right. The functional group for alcohol is an OH group. We talk about a hydroxyl group. All right. Here's another special reaction. Bromoethane with ammonia. We refer to as nucleophilic substitution of ammonia to form a primary amine. Okay, it's a mouthful. I'm not going to do it now. We will do it a little bit later on. I'll come back to nucleophilic substitution. All right. To form a primary amine, it's a protein molecule. Okay. Here we've done the addition or the reaction of the haloalkane with water in the presence of an alkaline substance. That's one way to make an alcohol. There are other ways as well. How do we do it when we make wine? Sugar or carbohydrate, it ferments. Okay, so the one way of making alcohol is to take the haloalkane and heat it together with water in an alkaline medium. That's one way. Another way is by fermenting natural hydrocarbons. Okay, we need an enzyme, yeast, for example, helps the fermentation along. All right, and then there is another way. When we have an alkene, we can go and add water to it. I just want to check something. My notes are, just hang on a moment. All right, I want to carry on. We've had a look at addition reactions onto alkenes. Okay, addition reactions onto alkenes, people. We said we can add hydrogen, then we get an alkane. We can add a halogen, then we get a haloalkane. Now, we've had a look at the formation of alcohol when we react the haloalkane with water in the presence of an alkali. Now, we can also make alcohol by the reaction of an alkene. Over here, we can have an alkene with water, and the product is an alcohol. And it is also an addition reaction. If I took ethanol, ethene, Janus, jy is die volgende ou wat gaan skuif. If I take ethene and I add water to it, all right, I am going to get, I want to write the water as HOH, like this, HOH, all right. We are going to get the following. Our double bond is broken. I should have done this in red, otherwise it's just easier to see where it goes there. That is the original part that we had. We broke the double bond, so a bonding place opens up, and we go and add, come on, a hydroxide, and that is an alcohol. Yeah, because we break the double bond and two bonding places open up. Yes, that's why alkenes are more reactive. Okay, and there isn't a byproduct that you have to worry about. And they are, that is why they use them. Okay, so very important, people, we can make alcohol three ways. One way is by Fermentation. One way is by fermentation. Fermentation was when we said sugars react, carbohydrates. I've not drawn you the reaction. No. Okay, so carbohydrates, they can, in the presence of an enzyme, forms alcohol and carbon dioxide. All right. Or we can make alcohol by reacting a haloalkane in the presence of an alkaline. We boil it together with water. That can also form alcohol. And lastly, we can add water in the form of steam. All right? And usually there's an acid catalyst, something like phosphoric acid, is added onto the alkene and it forms the alcohol. In this case, ethanol, because my alkene was ethene. All right. Okay, now, I'm in your textbooks. They're on page 133. There they have addition of bromine, they have addition of hydrogen, and they have addition of water to the double bond. All right, that is very important. Now, ethanol is very useful. In your textbooks, there on page 134, they have a heading. It says, a renewable fuel, ethanol. Now, if I take crude oil, my alkane, and I make an alkene by cracking it, are you with me? And I go and I add water onto the alkene and I make ethanol. Is that renewable? No, because I used crude oil. But if I use pineapple skins and I allow them to ferment and I get ethanol, is that renewable? Yes. All right. So in terms of ethanol being renewable, it depends on from where it was made. What was the production process? All right. The one process is renewable, the other one is not. No. And that is why diesel, you can make diesel from castor seed oil, sunlight seed oil, soybean oil. Okay, any oil you can make diesel from it. Then it is renewable. The moment you use crude oil, it is non-renewable. So why don't they use sunflower seeds to make diesel? No. It's not impossible. The problem is it starts competing with food supplies. In a first world setup, it's possible to do. But in a third world setup, you can't do because the people are already dying of hunger. Now you get farmers, instead of planting maize for milli meal, they are going to plant sunflower seeds for diesel because it's a better price thing. And that is why they don't do it. In terms, there are some countries that do it. Yes. Yeah, people, you can do it on your own small scale. Yeah, but that's the different process. Yes, that is just using old oil, and they, well, put it through a process, and it is converted to diesel, and it can be used quite successfully. There's a lot of people that, at one stage, it was very popular to do it. Yeah, it's diesel. I think. All right. There was, it's a couple of years ago, maybe about 10 years ago, it was very popular. A lot of people were doing it. Now it's sort of quietened down. I think it depends on your circumstances. If you don't have money for petrol in your tank, and you've got the know-how to go and collect old oil from restaurants, and you can produce your own diesel, then yes, it's worth the effort. But most of the people have got enough money to put the diesel in the tank. So it's really a big effort after they've done their normal work to go and do that as well. So I think it is still done, but it's not as popular as it was at a certain point. Okay. I don't know what the exact process is, but you can get it online. It's freely available, and it's not a very dangerous process. Yeah. Yeah. Yeah, it's a good diesel. Yeah. It is. Okay. So, people, alcohol then can be made using various methods. Now, in your books there, just a heading, ethanol as a renewable fuel. People, ethanol is used in, it's used as a solvent, paints, medicine. It's used as sterilizing. If you want to when you get an injection, they rub you with a bit of ethanol to sterilize the skin. No, the little thingy that they tear open, the wet tissue paper that they rub on. Yes, it's that. It's actually surgical spirits. It's probably not ethanol. It's probably methanol. Okay, the methanol, the purple spirits you buy in the shop, looks like this. Okay, it's only got one carbon. Ethanol has got 2 carbons. It also makes you drunk. Okay, it's very cheap, so people drink it. That is why they put the purple coloring into it. If you go to the doctor or a nurse, they will have a bottle of surgical spirits and it will be colorless. Okay, it's methanol. They use it to sterilize your skin for injections or whatever. Okay, the reason why the commercial one that you buy in the shops is purple, they add the purple pigment to it because it's got a bad taste, to discourage the people from drinking it. But they've discovered if they pour it through bread, it filters it out. It's a dye that they add that's got a bad taste. Okay. If you work with spirits, just wet your thumb and lick it. You will taste it's really unpleasant. Okay. Yeah. It is to discourage you from drinking it. But they do drink it. Okay. People who drink spirits, you can see them, they have lots of liver damage. You can very often see their eyes are yellow, the whites of the eyes, and they are also swollen. They look as if they are fat, but they are actually swollen. Okay? And that is from liver damage due to that one, methanol. Methanol can kill you. It can make you blind, and then, well, it does a lot of liver damage. No. In the Cape, in the Cape, it's a big thing. Yeah. I don't know. I don't want to try it. They do use it. So methylated spirits is also used as a fuel. It's used as a solvent. It burns, spirits burners. It is also quite a useful alcohol used in paint industry, used for soap, making dyes, etc. All right. And then there on page 135, making ethanol. Ethanol is made in 2 ways, actually 3 ways. The other way was the haloalkane with an alkali. And then over here, the one is fermentation, and the other one is the reaction of steam onto the alkene. All right. Yes, you must know. All right. Your syllabus specifies that. Yes, in the presence of an alkaline substance. Yeah. Okay. Well, ethanol, they have got, when you add water to it, steam in the presence of a phosphoric acid catalyst usually. Okay, so please take note of the reacting conditions. Ethene is heated to 300 degrees under pressure with steam and phosphoric acid as a catalyst to make ethanol. All right. I would also not like to drink this ethanol made this way, because what's the origin? Crude oil. Technically, it's the same thing, but I don't know if I would like to drink it. You know, yeah. It's just, yeah. The one that we drink is the one that is fermented naturally, or helped along, but it's the fermented one. No. Okay. Then, okay, here we've got nucleophilic substitution. Okay, I can go back to my notes. All right. Now, we must have a look at polymerization. Now, how does polymerization work? Now, a polymer is simply a long chain-like molecule. All right? Now, polymerization, we get two basic types. The one, we simply add one molecule onto the other. We call it addition polymerization. Now, which substances underwent addition reactions? The unsaturated ones. So addition polymerization implies that you've got an unsaturated compound where you will break the double bond, two bonding places will open up and the molecule can attach itself. This building block, we talk about monomers, can attach, okay, to form a polymer. Now, one of the most commonly used polymers that are formed as a result of addition polymerization is something called polythene. What is polythene? No. Polyethylene, it's the stuff you cover your book with. It's plastic. Okay. So, polythene, the building block is ethene. Okay? And what we go and do is, we go and break the double bond. So, there, usually using high temperature and high pressure. So this is the building block. So they are going to attach onto each other by means of addition reactions. How do we write this reaction? Well, this can go on into infinity. So we say we need an n number, a whole number. Can be very large, can be smaller. And what we go and do is we get a chain that is going to be n carbons long. Yes, because you open up the bonding place. No byproduct. Well, sometimes you do have it, but yes, in this one there isn't a byproduct. It's simple addition polymerization. Yes. Yeah, and it's going to be harder to get it to go because the alkanes are less reactive. Okay, so it would probably require much higher temperatures, much higher pressures. It might require ultraviolet light. It might require different catalysts. Okay, it's just much easier with the alkene. Yeah. Okay, and it's quite simple to make an alkene from an alkane. Yeah. Yes. Yes, it does. That's the building block. That's the monomer unit. In other words, we are going to get, and here's the second one. Let's go there. There's the third building block. Do you understand? And this is going to carry on into infinity. Yes, it does. Yes, it does. Softer plastic, thicker plastic, harder plastic, plastic that can